In this video, I will show you how to plan and simulate a 5th generation district heating and cooling network with the nPro tool. We will go step by step through the calculation process and create a 5th generation district heating and cooling network for an exemplary district. Hi and welcome to this nPro tutorial. I'm Marco, and in this video I will explain how you can use nPro to simulate a 5th generation district heating and cooling network. If you don't know what a 5th generation district heating and cooling network is, have a look at our website. There you find a lot of information about this new type of heat network. Alright, let's have a look how the calculation works in nPro.
To plan a 5th generation district heating and cooling network, we use the module load profiles and heat network. Here we create a new project. We can enter a project name, and here we have to select 5 GDHC energy network. We can change the location. I stick with Berlin, Germany, and say create new project. On the bottom, we have the section where we can define new buildings. We can enter a building name, a floor area, and then define the building type. And here I use residential building, and let's take some specification here, multifamily house. And if we don't know what's the demand of a multifamily house in Berlin, that is residential, we can click on insert default values, and then nPro inserts the values that are in its database. So here it's 98 kilowatt hour per square meter and year for the specific annual demand. And for domestic hot water, it's 21 kilowatt hour per square meter and year. Of course, we can change these values if we want to. On the bottom, then we have the building energy system section. That is only the case if we have a 5 GDHC network, so a 5th generation district heating and cooling network, because there we have the decentral heat pumps in every building. And we have to define how these heat pumps should be calculated. We can have a constant COP, that would be the easiest case, but we can also use product data. For example, Budero's heat pump. We have to define the supply temperature, 35 degrees Celsius, for example, for a floor heating system. We can enable a heating curve so that the supply temperature decreases if the load decreases. We could also install an electric heating rod. So if we say, okay, the heat pump should not cover the entire heat demand, then we can say, okay, the peak capacity or the peak demand should be covered by this heating rod. So electric heater. Then for domestic hot water, we also have to define a COP. Let's select the same heat pump as for space heating. We define the supply temperature, and here we see also the COP. So for domestic hot water, it's 3.8 because we have a temperature lift from 16 to 60 degrees Celsius. 60 degrees is the supply temperature of domestic hot water, and 16 degrees is the network temperature of our thermal network. For cooling, we can either select a passive cooling option, so that's a heat exchanger that uses a cold pipe of the network to cool the building. Alternatively, we could have a chiller. Then we have to define the COP. And in addition, we can also enable an air-cooled chiller to cover peak loads. So for example, in summer, maybe it would be beneficial to have this peak load chiller to not feed all the waste heat from the cooling into the heat network, and maybe directly dissipate some part of the cooling load to the ambient. But to keep things simple, I will just use the passive cooling option in this example here. Then we can click on calculate demand profiles and then on add building to district. And then we see now we have one building in the building list. It's a residential building. We see the floor area and we see the heat and the heat demand. And this heat demand is not the heat demand of the space heating and domestic hot water, but this heat demand is the heat that is transferred from the thermal network, from the heat network to the building. And this is a little bit lower than the actual heat demand of the building. And I will explain why this is. If we click on show building details, then we see the key facts of the building. And here we see, okay, we have 980 megawatt hours of space heating demand and 210 megawatt hours of domestic hot water. And so that is more than 1000 megawatt hours, obviously. But the annual import of heat from the 5G DHC network to the actual building is only 918 megawatt hour. And the difference, the reason for this difference, there are two reasons actually. The first one is that the heat at the evaporator of the heat pump is not the same as the heat at the condenser of the heat pump, because the heat pump uses electricity. So the heat taken from the network is a little bit lower than the heat demand of the building. And the second effect is that we have an internal building demand balancing. So for example, in summer, we have a cooling demand and a domestic hot water demand. And if these demands occur at the same time, we can use some parts of the waste heat of the cooling process at the evaporator of the heat demands to cover the domestic hot water demands. So with this, we can reuse waste heat from the cooling process to cover heating demands. And in this case, it's 48 megawatt hours that we can use directly at the evaporator of the heat pump, and that reduces the demands that we have to take from the heat network by 8.2%. You find more information on our website about this balancing effect and the energy flows in this system. Then we see the table with the heat generation, the seasonal COP here, the cold generation. It was only one building, so it's pretty straightforward. And we can also visualize the different demands. So for example, here we have the space heating and domestic hot water demand. If we click on energy import, we see how much heat is imported from the or transferred from the heat network to the building, here in red. And we can also have a look at the annual profile or the heat map. So then I would like to show the results summary. We click on this button. Then we see the list of all the energy flows. We have the heat demand of all the buildings. That straightforward. We have space heating, 980 megawatt hours, 210 megawatt hours for domestic hot water, and that adds up to 1190 megawatt hours for the heat demand of all buildings. Again, in this case, only one building. The electricity demand of the heat pumps is 224 megawatt hours, and 48 megawatt hours could be balanced inside the buildings. So if we add these numbers and we end up with 918 megawatt hours for the heat that is transferred from the heat network to the building. If we have more than one building, we can have a balancing effect also between buildings. So waste heat from one building can be used in another building to cover heat demands. And then this number would not be a 0, but would indicate how much we can actually balance. If we have not insulated network, we can have heat losses. And then the final number for the energy hub is 918 megawatt hours in this case, which is then the heat that has to be covered at the energy hub. So it could cover from geothermal energy or from a waste heat source, for example. For cooling, it's basically the same. We have the cooling demand. Here in this example, we only have space cooling. We subtract the balanced demands in the buildings, and see then 152 megawatt hours have to be transferred from the network to the building. We don't have any balancing between buildings, and we don't have heat gains. So that is also the same number that we have at the energy hub. For electricity, we see that we have some electricity demand, so for lighting and computer infrastructure, etc. That is 220 megawatt hours. That's what we defined to create the demand profiles for electricity. We didn't consider any e-mobility. We have to add to these 220 megawatt hours the 224 megawatt hours for the decentral units, and this is the heat pump or the heat pumps in the buildings. We have then that 444 megawatt hours have to be imported to the buildings, so that's the load of all buildings. And then we add the pump work, which is here 11 megawatt hours, and see that at the energy hub we have an electricity demand of 454 megawatt hours. The energy flows and the reduction over the different stages is visualized in this plot here. So we see the, for example, the building, the internal balancing of demands in the buildings from the second to the third column, and the balancing between buildings from the third to the fourth column. The feed-in of heat and cold is visualized in this plot. So when do we need heat, when do we need cold over all month. Then again a table with the installed capacities for heat pumps and the heat exchanger. And finally, I would like to show the 5 GDHC network settings. So we can define the network temperature, the pump work percentage, and a diversity factor. For example, we enter 0.85, and then we click on show profile. And then we see, for example, in this section here, that the so gray is the demand at the energy hub without the diversity factor, and in red we see the load with the diversity factor. So the peak is reduced by 15% in this case, and the annual energy is of course the same with and without diversity factor. The pipe dimensioning. So in nPro you can calculate the pipe diameters and optimize them. If you have a star topology of the network, in this case we only had one building, so that was very straightforward, but we can dimension this section or this pipe. We click on pre-dimensioning, then we see, okay, nPro says, okay, around 100 DN 100, so 100 millimeters would be a good estimate. And then we can click on calculate detailed analysis, and then we get an overview of the pressure gradient in this pipe over the entire year. And here on this table we have some KPIs And we see that for DN100, we have a maximum pressure gradient of 228. So that looks pretty good for the sizing. If we want to be more on the safe side, then we could also use a 125. Then we would have a even lower maximum pressure gradient. We can download all the results of the single buildings on this button here, but on the big large button we can say download results of the entire district. This can be an Excel file, but also CSV files for all the time series and so on. In the Excel file, we have all the key results that I showed now, but also time series for the load at the Energy Hub with an hourly resolution.
If you have any questions or remarks about this video, feel free to leave a comment. If the video was helpful for you, please give us a like and subscribe to our channel. Thank you for your interest and see you next time.